The position of the sucker affects the turning effect. At the beginning of the video, the pulling force is applied further from the hinge. The turning effect is large. Then the sucker is closer to the hinge, and a larger force is needed to open the door. Lastly, when the force is applied at an angle, the needed force is also larger. So the direction of the force is also important, because only the perpendicular component of the applied force may produce a turning effect. The turning effect is measured by the moment of force, or torque, which is the product of applied force and the perpendicular distance from the point of rotation. It is a vector with direction either clockwise or anti-clockwise, as shown in figure 5.1b below. Note that the unit of moment is Newton meter, but not Joule, although moment and work are both products of force and length. The perpendicular distance of the applied force from the point of rotation is called moment arm. The size of moment arm depends on the point of action and the direction of applied force, as illustrated in figure 5.1a below. On the left, the moment arm is L and the force is F, and so the moment is FL. In the middle, the moment arm becomes L sine theta, and so the moment is FL sine theta. If you find it difficult to find moment arm, you may find the perpendicular component of applied force instead. So in this case, the perpendicular component of applied force is F sine theta, and then the moment arm is L. So the moment is FL sine theta. Easier, isn't it? On the right, there is no perpendicular component of force, and hence the moment is 0 in this case. The concept of moment does not only apply to the rod, but to any object, because any object may be turned, right? In figure 5.1c, the irregular rigid body experiences a force F at a point away from the point of rotation. First, the force creates an anti-clockwise moment about the point of rotation, and the moment equals F sine theta multiplied with the moment arm L, and therefore FL sine theta. The point of rotation is also called pivot. Can you identify the pivot in the following cases? And what about the moment in each case? Example 1. Pushing a door. Find the moment produced by the applied force in these cases. We have mentioned that a long lever may multiply the turning effect of a applied force. And now you may tell that moment is the product of force and moment arm. A longer tool may produce a larger moment to open the can. Try checkpoint 1 below.
Attach a rubber sucker to the edge of a door. Then hook a spring balance to it. Pull the spring balance along a direction perpendicular to the door. Find out the force needed to open the door. Attach the sucker closer to the hinge of the door and open the door again. How does the force needed change as the distance between the sucker and the hinge decreases? Now, attach the sucker to the edge of the door again. Apply a pulling force at an acute angle to the door. How does the force needed change?
Chapter 5. Moment of a force. 5.1. The turning effect of a force. Without a screwdriver, many of you may have tried to open a can using fingernails, and it mostly fails and hurts. The screwdriver, especially a larger one, can open a metal can at ease. Why? A screwdriver cannot multiply our work done, as conservation of energy does not allow. But surprisingly, any long object used as a lever in this way can multiply the turning effect of the applied force. 1. Moment. A force can produce acceleration, which Newton's second law have told us. The force may also make something turn. The turning effect increases with the magnitude of force and a physical factor. Let's take a look of experiment 5a to find out what the physical factor is.